all of our session speakers are here. Let's go ahead and get started. Okay, welcome everyone to our session. It's titled Judgment and Decision Making. We have an exciting lineup of papers, 6 papers to present in this session. And if you are watching the YouTube live stream, when you have a question to the speaker, please post it right during the talk. So there's a delay on Slido. If you post it at the end of the talk, we may not get to your question in time. So there's about a minute delay. So if you have a question for the paper for the speaker, please post it right when you have that question in your mind. Okay, without further ado, let's start with Başak. So the title of the first presentation is Decoupling Judgment and Decision Making, A Tale of Two Tales. So I'll let the speaker introduce himself and his co-authors. Go ahead, Başak.
Thank you, Wenyuan, for introducing me. Let me share my slides. Is everything all right?
Yes, loud and clear. Good.
Okay. So hello, everybody. I am Başak, and I use she and her pronouns. I'm a PhD candidate in Visualization and Graphics Group at Utrecht University. And today I will tell you about our work, which investigates whether decisions differ from judgment in data interfaces. When I started my PhD in decision-making with data interfaces, I was curious about what exactly makes something a decision. The terms decision and judgment are frequently used in the literature, sometimes interchangeably and other times distinctly, which creates some confusion. And I often ask myself, am I making a decision here or just thinking through my options? This made me wonder where a judgment does end and when a decision does start. I couldn't find a clear answer, and that led me to the research I'm sharing today. First, I want you to think about this question. Do you think this is a judgment? However, many people also tend to call those type of questions decisions in their daily life or even in the literature. We started with searching for definitions in visualization literature, but we couldn't find a clear distinction between judgment and decision tasks. So we turned to psychology and economics, where researchers have been studying the difference between judgment and decision-making for a long time. The American Psychological Association provides 2 separate definitions for judgment and decision-making. According to the APA, judgment is the capacity to recognize relationships, draw conclusions from evidence, and make critical evaluations of events and people, or the ability to determine the presence or relative magnitude of stimuli. In contrast, decision-making is a cognitive process involved choosing between alternatives. However, these definitions are not directly applicable to visualization because they are too broad to translate into specific task definitions. So we reviewed more studies and identified 4 key features that help separate decision-making from judgment. Here is what we found. First, a decision means picking one option while letting go of others. Second, decisions involve feature-oriented thinking. Third, when you make a decision, there is usually an expectation that you will act on it, whether that means doing something or mentally committing to a choice. And finally, decision-making often implies personal responsibility, which may not apply to judgments. With these 4 features in mind, we consider the difference in meaning between decisions and judgments. Now, we aim to explore if decision accuracy differs from judgment accuracy in practice. To explore this, we designed 2 experiments. Our goal was to see even a small change in how a task is framed would make a difference. We presented both judgment and decision tasks in 2 different contexts. First, fantasy sports, where there's a fantasy sports team that can buy players to increase its chance to win the games. And second, humanitarian aid, where an imaginary country in war, Moldavia, seeks for help from external organizations for the orphan kids. For judgment tasks, we asked participants, what is the best option for a team owner or a country? Here, you see an example stimulus from a judgment task in humanitarian aid context. The title row includes the question at the left column and the header for cost profit and probability columns. The next 5 rows show the alternative options. For example, here, the first row shows a statistical option, which is keeping the current status as it is. And the second row shows an external humanitarian organization called EKO with its expected outcome on the other 2 columns. Third and the other 2 rows show other possible humanitarian organizations with their different expected outcomes. After observing the presented information, participants indicated what they think the best option is for the country among the 5 alternatives. In the decision task, we asked, what do you choose? This question encouraged action, which is a key part of decision making. Here, you see an example stimulus in fantasy sports context. Same with the judgment task. The title row includes the question at the left column and the header for cost profit and probability columns. Again, the next 5 rows show the alternative options. For example, here, the first row shows a player called Norbert and the expected outcome of his addition to the team. And the second row shows a statistical option, which is keeping the team as it is without adding a new player. Third and the other 2 rows show other possible players with their different expected outcomes. After observing the presented information, participants choose what they prefer among 5 alternative players for their team. We also explored whether different visualizations, dot plots, density plots, and probability bars influence participants' performance. Now I will show you the main findings, but for more details, please refer to our paper. In experiment 1, we got inconclusive results, which appear to be due to our both tasks being too easy. So we increased their difficulty in experiment 2. Here are the results of experiment 2. The blue and red points on the left represent the average accuracy scores, with the lines showing 95% confidence intervals. And on the right, we see the mean difference between judgment and decision accuracies, along with 95% confidence interval. The D represents the coherency effect size, which indicates the strength of the difference. If we look at the 95% confidence interval with mean difference on the right, the black one, we see some evidence that decisions are more accurate. The difference was most noticeable in the humanitarian aid scenario and when using the probability bars compared to other 2 visualizations. Additionally, we observed more statistical bias in the judgment task. In our experiment, statistical bias refers to the tendency to keep things as they are without actively seeking a new player or an external humanitarian organization. These results was also aligned with what one participant reported in a previous interview. A decision maker has to live with their decision, while an analyst can just say what the best thing is and walk away, which suggests that decision tasks may encourage action, pushing participants to avoid sticking with the default option. So what do these results mean? Even manipulating only one differential feature of decision-making in our task framing, we saw some evidence of a difference between judgment and decision accuracies. Yet, some confusion between the terms may exist not just in the research community, including ourselves, but also among participants. The textual analysis of participants' open-ended responses did not reveal difference between the language participants used for judgment and decision-making, which could simply relate to the alternative choice format rather than being indicative of a high-level strategy. On the other hand, a previous study also used a similar framing with our experiments. For example, in analytic framing, they asked participants, given what you read, select a house that is a good deal. Or in decision-making framing, they asked, given what you read, which house would you buy? But the direction of the difference was opposite to what we observed. As you can see from the confidence intervals at the bottom, when participants were framed as real estate analysts, they perform more accurately than when they were buyers. Although we are confused by the direction of the effect, these results show us that these two terms are distinct and cannot be safely used interchangeably. Yet it's hard to observe where this separation starts, and it remains an open question. So if you have an answer, I would like to discuss it with you. Finally, I would like to thank my co-authors Pierre, Alex, and Evanthia. Before I finish, also there's an open PhD position in visual analytics for explainable visual rehabilitation in my research group at Utrecht University. You can scan the QR code for details if you are interested. Thank you for your attention, and I am happy to take any questions.
Okay, thank you, Başak. We got 3 questions coming in. The first 2, I see they're related. So intuitively, what does it mean for a decision to be more accurate than a judgment?
That means in our experiments, for both tasks, we defined a same accuracy metric. And the accuracy metric is, as you can see from the tables from the previous slides, there was row for example, in fantasy sports scenario, the first row is the name of the player, and the second row is the cost and profit information, and the last row was the probability information. Then for each alternative, we calculated a normative accuracy metric for both judgment and decisions. And then, based on participant responses, we calculated some proportion between how far participants respond from the worst option and also the best option. And we then compare these 2 accuracies to each other. So that was the accuracy metric for judgment and decisions.
Okay. And really quickly, the second question, would you
Yeah.
perceive the results to be more beneficial for deciding how to frame the tasks in visualization studies?
Can you repeat the question?
So how would you sort of inform the framing of the tasks in
Yes.
sort of future visualization studies?
Yeah. Indeed, what we identify is there was not clear definitions of the judgment and decisions. So that was the first observation that we found during the literature review. And then that was the reason why we also tried to find some distinctive features of decision-making and judgments. And then we implemented our experiments based on these distinct features. And we observed that even manipulating one of them in our task framing indeed created some difference. But as I also said at the end, that we need more studies on top of it to come up with a shared and extended definition of judgment and decisions.
Thank you very much for the insightful talk.
Thank you.
All right, let's move on to our next exciting presentation. The title of the presentation is Unmasking Dunning-Kruger Effect in Visual Reasoning and Visual Data Analysis. Our presenter is Mengyu Chen. I'll let her introduce herself and her co-authors.
Thank you, Wenyuan. Can you hear me clearly?
Yes.
Okay, so hi everyone, this is Mengyu. I'm so excited to share our findings on masking Dunning-Kruger effect in visual reasoning and judgment. Here, I'd like to thank my collaborator, Inji Liu, and my advisor, Dr. O. Today, I will cover 4 parts today. First, I'll introduce what Dunning-Kruger effect is and why we investigated Dunning-Kruger effect within visualization and what research questions we are interested in, followed by our study design, and finally, I'll share our findings. So, this graph shows how confidence fluctuates as knowledge accumulates. Have you ever noticed how some individuals consider themselves experts when they are far from it, or how the truly skilled people often underrate their abilities? That's the essence of Dunning-Kruger effect, which I will refer to as DKE. DKE is a metacognitive bias where those with limited skills often overestimate their competence, but the highly skilled people tend to underestimate theirs. Such overestimation and underestimation have been found in contexts like second language learning, medical residence training, and face perception abilities. But it hasn't been thoroughly explored within the visualization community, where the domain expertise is much like having a navigational compass which guides you to make informed decisions based on prior knowledge. But a twist arises when individuals fail to accurately gauge their knowledge levels, leading to potentially flawed decisions. So this is particularly risky in fields like healthcare, public policy, or business intelligence, where the data-driven decisions are crucial. In this work, we centered our investigation around two research questions. First, can we detect the classic DKE trend within the realm of visualization? If it exists, what might indicate the presence of DKE in this context? We are exploring whether interaction patterns, personality traits, and domain familiarity could be linked to the manifestation of DKE. To explore these questions, we conducted two studies. The first one involved visual reasoning, where participants were asked to complete a personality trait survey first and then complete a 15 puzzle game, where the goal was to arrange numbers in sequence with the fewest moves. We recorded their interactions with the board, like which tiles they shuffle around and where they put the tiles. Then they were asked to estimate their performance and domain familiarity in a post-survey. The second study mirrored the first one, but it centered on visual judgment, where participants were asked to categorize data points based on specific criteria within two different domains, their card type and credit level. We also recorded their interactions, including attribute selection along the X and Y axis, and their points engagements like hovers, clicks, to see how they approach the categorization task. Our analysis of DKE involved comparing actual and perceived performance percentile, particularly focusing on the top and bottom quartile. In this line chart, a blue line represents an accurate self-assessment of performance. A yellow dotted line shows the perceived performance percentile. And the green color here indicates perceived reasoning ability. In study 1, participants in the bottom quartile on the left side, who ranked in the 10th percentile for actual moves, perceived themselves to be in the 40th percentile. But top quartile participants on the right side with actual performance in the 85th percentile underestimated themselves at 65th percentile. And this trend of misjudgment also extends to perceived reasoning ability. We likewise observed DKE for both the car and credit categorization task in study 2. For example, participants in the bottom quartile of the car task in the 15th percentile overestimated their accuracy at 42nd percentile, but participants in the top quartile who scored in the 90th percentile on average significantly underestimated their accuracy at 37th percentile. So across two studies, we consistently observed a classic DKE pattern where both top and bottom performers systematically miscalibrate their abilities. Besides the replication of DKE, we have hypotheses about the relationship between performance and interactions. For example, the sequence of things people clicked on, their personality traits like extroversion or conscientiousness, and their domain familiarity, ranging from 1 indicating not at all familiar to 5 means extremely familiar. To see if top and bottom quartile performers approach tasks differently, we analyzed their interaction patterns tailored to each study's nature. In study 1, we visually examined the interactions of participants in 4 quartiles using line overlaid on the puzzle grid to show their movement path, where the line thickness here indicated the frequency of tile movements in specific direction. we found compared to the top quartile participants, bottom quartile often move types randomly. So it suggests the potential link between skill levels and interaction strategy. In study 2, we broke down our analysis into 3 aspects of interactive behavior. Interaction rate measures the number of interactions per second, but we didn't observe significant difference in interaction rates between top and bottom quartile in either task. The think time metric defined as the interval between 2 consecutive interactions. It showed a significant difference in the credit task only, where the top and bottom quartile participants varied notably in their decision-making speed. For interaction sequence, we computed the frequency of one interaction type succeeded by another interaction, and no significant difference was found between bottom and top quartile in both tasks. So we found that the 2 groups performed the puzzle game in study 1 differently, but we observed relatively little distinction between interactive strategies of top and bottom quartile in the categorization task. So it's necessary to isolate factors such as task difficulty, which might cause inconsistencies in observed differences across some measures of interactive strategies. We then compute a Pearson correlation analysis to assess the relationship between individual personnel traits and susceptibility to the DKE. We use the difference in perceived and actual performance as a measure of susceptibility. In study 1, only conscientiousness showed a significant impact, with higher score correlating with a greater tendency to overestimate performance. In study 2, conscientiousness again had a noticeable effect, but only in the card task. It's the same, with higher scores correlating with a greater tendency to overestimate their performance. So we observed that conscientiousness correlated with susceptibility to DKE in both study 1 and the card task of study 2, that is, with higher scores correlating with a greater tendency to overestimate performance. We then explored the relationship between self-reported domain familiarity and the presence of DKE, here still using delta performance as a measure of susceptibility to DKE. In study 1, no significant correlation was found, but in study 2, we observed a significant positive correlation, that is, higher familiarity level correlates with a greater tendency to overestimate performance. So we found that individuals with higher self-reported familiarity in a specific domain were found to overestimate their abilities. But the absence of a significant correlation in study 1 might imply that this correlation may not hold universally across different domains, or there might be other factors could affect the accuracy of self-assessment. So in this work, we observed differences in interaction patterns as well as some personnel traits across different proficiency levels. These findings suggest potential applications such as personalized guidance and bias mitigation by adapting to a user's proficiency levels and personnel traits. In our paper, we discussed these implications by demonstrating how an analysis tool could dynamically adjust to an individual's susceptibility to biases like DKE. So I hope this presentation sparks your interest in how cognitive bias like DKE can play out in evaluation, and more details can be found in our paper. I look forward to any questions you might have. Thank you.
Thank you, Mengyu. We received a few questions, and for the question, we only have time for one quick question. For the rest of the questions, please take to Discord, to the Discord channel. Very interesting work. So what are the implications of this work on studies of graphical literacy?
Sorry, what was the question?
So what are the implications of this work on sort of studies of graphical literacy, how people read graphs? So would you say how to incorporate, would it be helpful to incorporate personality traits and DKE and the relationship, since you found a relationship between those?
Well, thanks for the question. Yeah, so as for the implication, we discussed that this could be a benefit for future personalized guidance and also incorporate the personality traits when designing the tools. And as for the implication, well, because in the seminal paper that by Dunning-Kruger, they attribute the DKE phenomenon to a lack of metacognitive ability. So personally, I think it would be interesting to see how we can improve metacognitive skills in this context, where I believe both VIS designers and viewers could have roles to play in this process. For designers, we could create tools and interventions to help viewers gain clear and accurate awareness of their abilities. And this could involve design more intuitive visualizations that come with guidance on how to interpret them correctly, or integrating features that prompt users to reflect on their abilities before reflect on their understandings before drawing conclusions.
Okay, very interesting. Suggestions. Okay, very good. Thank you.
Thank you.
I see a lot more questions. Please take them to Discord. Let's move on to our next exciting talk. The title is Trust Your Gut, Comparing Human and Machine Inference from Noisy Visualizations. And our presenter will be Ratanond Koonchanok. I'll let him introduce himself and his co-authors. Please take it away.
All right. Hello. Can you see my slide? All right.
Yes, very well.
All right. I am Ratanond from Indiana University, Indianapolis, and this is a collaborative work with Argonne National Lab and University of Illinois at Chicago. Okay. One second. Just try to minimize the. So suppose I give you sample data that displays the relationship between sugar consumption and height. What would be your inference from this data? If I give this data to a statistical machine, it will give strong evidence that the true relationship is positive. However, a human would suspect that the pattern is a bit extreme and could be spurious, so they might infer that there is no relationship. And it turns out that the visual inference by human, while statistically irrational, is closer to the data generating model. This shows that a deviation from the statistical inference can sometimes be productive. Such scenario motivates us to understand how deviations from statistical rationality can be advantageous. While prior works consider smaller divergence from statistical machines to be more effective and seek to minimize human biases, we are interested in scenarios where human and machine inferences can complement each other. Our main hypothesis is that inference from extreme samples could be one of the cases where humans could outperform machines. In this work, we generate a range of samples from ground truth models and test how humans perform relative to idealized agents. Note that while majority of the samples are not extreme, the extreme ones could occasionally occur. We utilize crowd wisdom to generate possible ground truths for 24 pairs of attributes related to everyday topics, creating 24 questions in total. First, we ask, how do visual analysts compare to ideal Bayesian agents that see the same data? And second, how do sample characteristics affect inferences for both agents? In particular, we hypothesize that humans can be more conservative when encountering extreme samples. We measure extremeness using the difference between the expected R value and the sample R value, with the higher difference indicating more extremeness. Non-extreme samples are those congruent with the ground truth and will occur more frequently. As samples become more extreme, they become less congruent. These extreme samples are the ones we are particularly interested in. We conduct a crowdsourced experiment to obtain human inferences. Participants utilize an elicitation device to register their prior belief before seeing the sample and provide inference after. The human beliefs are also fed into the Bayesian model alongside the sample data to generate the informative Bayesian responses. Finally, we also have a flat prior model that learns from the data sample alone. To elicit human responses before and after sample exposure, we provide participants with a set of sliders to adjust the slope and uncertainty of the attributes. We also include the hypothetical outcome plots that enable them to observe multiple potential samples based on the elicitation. To present the results, we use the slope divergence as a primary metric. We define it as the difference between the inverse slope and ground truth. Similarly, we also define the uncertainty divergence as the difference between inferred uncertainty and ground truth. We first compare the divergence by agent type. Overall, the flat prior agent displays a lowest divergence from truth overall, while human displays the highest divergence. This is likely due to the fact that most samples are not extreme, giving an edge to the data-driven machine. However, humans exhibit the least sensitivity to extreme samples, as their divergence increases by 14.3% for each unit increase in extremeness, which is the lowest among all agents. We then compare human and machine performances by plotting the relative ratio between their divergences against extremeness. Specifically, we compute the log ratio of the two divergences. If the log ratio is positive, then it means there is less divergence for human inference and humans are more accurate. On the other hand, if the log ratio is negative, then there is less divergence for machine inference and machines have higher accuracy. Here we are showing human versus informative Bayesian. It turns out that when extremeness is low, the Bayesian machine provides a better inference. In contrast, humans become more accurate as extremeness increases. Note that the distribution of extremeness is not uniform, as shown by the distribution plot above. Extreme data naturally occur less frequently. Flat prior displays similar results, as shown by the gray line. Overall, the takeaway from this is that humans can be more accurate when making inference from extreme data, while machines are generally more accurate when data are not extreme, which means that human intuition can be advantageous even when diverging from statistical rationality. When looking at sample characteristics, we found that humans are more accurate when the ground truth consensus is high. High consensus means that there is a strong level of agreement among the crowd wisdom. We also found that participants who use icon arrays provide the most accurate inferences, although our visualizations are relatively close. Finally, our results indicate that humans tend to be overconfident in their inferences, as shown by the high divergence in uncertainty. The main takeaway from our study is that human analysts and statistical machines excel in different scenarios, and deviations from statistical rationality can be helpful at times, Specifically, human analysts show less deviation from the ground truth when making inferences from extreme data, as their internal model can help resist spurious samples. Our results pave toward designing visualization systems that promote human-machine collaboration, where there is a balance between rational and intuitive thinking. But there are still some challenges to overcome. First, it is not straightforward to know the extremeness of the data sample at hand. And second, there were a lot of variability among human responses, which could potentially be reduced by improving knowledge elicitation in visualizations. And that concludes my presentation, and now I'm happy to take any questions.
Okay, thank you for the interesting talk. So I have a question. So now you compare sort of human performs better when there's more extreme cases, more noise, and machine inference is better when there's less noise. How can you see them, like the human and machine AI working together?
I think it depends on the scenario. For example, the machine could, there were cases where data might be limited. For example, there are previous studies in like study of rare species of animals where data are limited, and usually domain experts need to borrow information from nearby species. So in that case, I think when data is limited, human can override the machine and use their intuition to make decision. On the other hand, when we have a lot of data and we can utilize the computational advantage of the machines, that's the case where machine can help us avoid bias in our decision.
Okay, they could kind of complement each other. I see a question on Slido. It's similar. I think it's similar to what I just asked. Please take it to Discord. And thank you, Ratanond, for the interesting talk.
Thank you.
Okay, and Arran, please get ready to share your screen while I introduce you. So our next presentation, the title is Causal Priors and Their Influence on Judgment of Causality in Visualized Data. I'll let the speaker introduce himself and his co-authors. Take it away, Arran.
Hi, folks. I'm Arran from UNC Chapel Hill, and the title of our work is Causal Prior and the Influence on Judgments of Causality in Visualized Data. I'll be sharing this work on behalf of my colleagues from UNC Chapel Hill, Renzi, and Davis College. Supporting causal inference for users is a fundamental pursuit of visualization and visual analytics. But how do people understand causality from charts is still a remaining concern. Correlation does not imply causation is a famous mantra. While visualization naturally shows correlation but not causations from its visual representations. So there comes a question like correlation does not imply causation, but what may lead to users' causality judgments in the visualized data? So if we take a step back, can people really infer causality from common charts? Let's see a very simple example. So this is a bar chart shows data of survival rates and cabin clauses in the sinking of Titanic. It's very common that users may judge the causation that cabin clauses cause different survival rates in the sinking of Titanic, and this is how a simple visualization can lead to a judgment of causality. While if you look at recent advances on the theoretic side, we found many interesting insights have been released. For example, statistical visualization may convey illusionary effect to users' causality judgments. Users may either under or overestimate causal linkages between variables when they are evaluating causal graphs. And users tend to assign causal effects to variables used to group data within simple bar charts or line graphs showing these counterfactuals. Well, all those fabulous past work triggered our core motivation, that is, what factors may impact people's perceived causality in those common charts. And to simplify this question, we are looking at a common statistical visualizations like this. This chart showing the data of computer speed and laptop price. People can easily draw a causal conclusion from this chart that a higher computer speed may cause a higher laptop price. And we hypothesize
such result could came to the impact of two factors. While the first one, we call it concept pairs, which is the semantic of words denoting what X and Y axis mean in this chart. Here, they are computer speed and laptop price. We anticipate there also exists a causal prior, which means the preconceived notions of causal relations. In this case, between computer speed and laptop price. We assume it may influence users' causality judgment even with charts. While the second part is the data being visualized. Here we call it as visualized association in our work. Noting that the perception of the visualization is also impacted by a lot of other things like annotation or tasks. But here we primarily focused on these two factors for simplification. So for uncovering their impact, we need to understand first, do people have underlying priors regarding the causal relationships between concept pairs? And second, if so, do those causal priors affect the interpretation of causality from realizations of those concept pairs? To understand these 2 points, we separate our work into 2 studies, where we have study 1 to identify causal priors for concept pairs, and have study 2 to investigate how causal priors and visualized association combined to impact the judgment of causality. For study 1, we hypothesized that people have underlying causal priors regarding the assumed causal strengths of causal relationships for concept pairs. And we collected a data corpus including 56 pairs of concepts from various resources, and we started to revise some of the names to make it easier to understand. We also designed a set of causality questions like, for example, how much will an increase in computer speed cause an increase in laptop price? And we also provided some background information for specific pairs, like the Titanic case, we provide information like in the Titanic sinking, or some other cases like in a cancer surgery. And users are rated their causal judgment in a 5-point Likert scale together with confidence rating. This study incorporated 100 ml Turk users, using here is an example of those questions. For the results, as we expected, we found that concept pairs significantly impact the perceived causality, along with many existing work on behavioral science. We ordered the overall results with an increasing average causal relationship regarded as causal priors here. To be more specifically, we can see people are more likely to converge their causality judgment to add concept pairs with both very high and very low causal priors, like how much ice cream sales causes shark attacks, or how much alcohol consumptions cause higher liver disorder severity. But for the middle pairs, we found the judgment could be more randomly distributed, like how much variable A causes variable B. So given those results, we go to study 2 to understand the impact of visualized associations together with causal priors. We employ the same concept pairs and same causality questions as study 1, and use the results of study 1 as causal priors for study 2. We also designed a set of visualization stimuli for this specifically. And the stimuli was designed using 5 different levels of visualized association, starting from 0 and ending at 1. Using 3 common chart types, scatter plot, line charts, and bar graphs, as shown here for some stimuli. Before the setting kind of things, we hypothesized causal priors and visualized associations will both impact people's judgment of causality with charts. And these could be somehow explained by their disagreement between the causal priors and visualized associations. We also anticipate the chart tabs could have a potential impact on their influences. So we have 250 ml Turk users and using like these examples. For the results, first of all, we found causal priors and visualized associations both significantly impact people's judgment of causality, aligns with the hypothesis. And for the disagreement, specifically, we found as we have stronger causal priors, we are less likely to be impacted by visualized associations. Let's see some examples. If you see this chart, we can get a very strong correlation from it. But what if we consume it in terms of causation? Let's combine with different concept pairs, like if it shows computer speed with laptop price, it seems plausible that people could judge higher computer speed cause higher laptop price. But if they are the consumption of mozzarella cheese versus the computer science PhD awarded in the US each year, so you may say it looks somehow weird and there may be something wrong here. This is literally what this finding tells us. And beyond which, for chart types, we found realized associations had a greater influence on bar charts and line graphs compared to scatter plots, partly support our hypothesis. And this insight also aligns with several previous studies which found similar impact on those charts. And finally, we examined the disagreement impact on causality perception, where we call them differential causality. The differential causality is calculated by the differences between users' causality judgments, causal ratings with our charts minus their original causal priors. And the disagreement is defined as the normalized differences between realized associations and causal priors on specific cases. For the results, we found something interesting effect where we call them as regression to the mean. These effects indicate that people tend to overestimate causality of concept pairs for concept pairs with lower causal priors, no matter what kind of realizations is showing. But for concept pairs with higher causal priors, people tend to underestimate the causality with any charts. And such underestimation or overestimation effect have also been reported by a recent causal support study, where our work may somehow reflect their findings. Regression to the mean also indicate that realized data may have a greater influence for concept pairs with the middle causal priors. And at last, we identify several key limitations in this study. First, we only have like 56 pairs, which is not a very large number, and it should be enlarged in the future. Second, our realization stimuli design is somehow restricted, like we all have limited 3 chart types. We don't have any negative associations. Third, we didn't consider some user background factors like expertise or visualization literacy, which may also have an impact here. And last, we believe the study could be improved by a more in-depth causality perception modeling methodologies using advanced techniques like mathematical, statistical, or cognitive methodologies. And finally, this work is not possible without our fabulous co-authors, and our work is supported by NSF. And thank you so much.
All right. Thank you, Arran, for the interesting talk. And to remind everybody who's watching the YouTube live feed, the questions will come in a delayed manner. So if you have a question to the speakers, post it right when it comes to your mind. Don't wait until the end of the talk. I'll ask a question while we wait for more questions to come in. My students always have this debate with me. When can we frame relationships as causal, and when should we only call it a relationship or correlation without saying it's causal relationship? I wonder if you like some of the pairs of parameters, yeah, that you use sharks and ice cream sales, shark attacks and
Yeah.
ice cream sales. It's hard to say they have a causal relationship.
Exactly.
Mhm.
I think this problem could, like in our study, because we only consider these 2 factors, so we assume, based on those user results, we assume if the concept pairs could probably handle causal priors, it could be more likely to judge as a causation instead of correlation from where we see from data. But if it's not, like ice cream sales example, we may say it's less likely to hint a causation here. But there may, for example, there may be some confounder effects like the hotter summer may cause higher ice cream sales, and meanwhile the hotter summer may cause higher shark attacks because more people go to the beach for their vacations, something like that. But what we also found from users' results is like here, even though those shark attack example is with very low causal prior, sometimes some users still tend to have assume a somehow higher causation if we are showing them with a very strong correlation in the data. So I think it really depends. It probably depends on users' personal expertise. Like if they're more expert, they are more likely to prevent themselves from those kind of effects. So this could also be related to some psychological effects like confirmation bias. I anticipate these kind of things could be explained by a deeper study if we incorporate more user background, user expertise, and realization literacy kind of things into this study. Yeah.
Yeah. Okay. Yeah. Very, very insightful. And another thing, very quick comment that we found was, it's also good to evaluate how personal invested the users are in a particular topic, right? If the user has a very strong prior, then it's very hard to move the expectation. So if you show a relationship that's incongruent with the prior perception, it's hard to convince the user otherwise.
Yeah. Also related, we also found like in those cases you just mentioned, people's confidence. Here is a result about confidence. As you can see from the leftmost side and the rightmost side, the confidence actually decreased no matter charts are showing. So this is you can find those results in the paper, but I think this could also relate to what you just said. Yeah, thank you so much.
Okay, very good. We're doing great on sort of time management.
Yeah,
thank you, Arran. So Adam, please share your screen. Our next presentation is Knowledge Viz, interpreting language models by comparing fill-in-the-blank prompts. So I'll let Adam introduce himself, his co-authors, and carry on with the presentation. Take it away,
All
Adam.
right. Great. Thank you very much, Wenyuan. So yeah, we're going to be shifting gears into LLM evaluation, which might be a little different from the topic here, but we'll probably find some overlaps as we go. So hi, everybody. My name is Adam Kasha. I'm a fifth-year PhD student at Georgia Tech. Along with my co-author, Alex, I'm excited to present to you Knowledge Viz, a visual analytics tool for interpreting language models by comparing fill-in-the-blank prompts. So let's consider sending two fill-in-the-blank sentences. A woman is meant to be blank and a man is meant to be blank as prompts to ChatGPT. What do you think it's going to return? Well, when we ask LLMs to fill in the blank, their responses can reveal learned patterns and associations, including harmful stereotypes and biases. And so I was playing around with this and I thought to myself, hey, can we build a tool to evaluate LLMs by interactively comparing fill-in-the-blank sentences? And I was inspired by this Google Pair Explorable, which was written by Adam Pierce in 2021. He used pairs of fill-in-the-blank prompts to visualize the likelihood of Bert's predictions, revealing associations with each sentence that give us insights into what Bert has learned in his pre-training. And I wanted to take this to the next level, and so I asked, how can we visually compare more than two fill-in-the-blank sentences at a time to evaluate LLMs? So to make this work, we needed to solve a few design challenges. Our solution would need to support visual prompt engineering, as well as grouping of prompts and predictions for making sense of the data. And we would then need visualizations that could compare n by n sentences with up to k predictions per sentence. And our solution, Knowledge Viz, is a human-in-the-loop visual analytics system for comparing fill-in-the-blank prompts to uncover learned text associations in LLMs. So it helps users rapidly prototype multiple fill-in-the-blank prompt templates, group sets of results by sentence, and clusters predictions by shared semantic meaning, and then visualizes different associations that have been learned across 3 plots. So let's dive into each view in detail here. The prompt interface allows users to input as many sentences as they want, and the users then type sentences with a subject mask and multiple replacements for that subject. Then the visualizations will group the results by each replaced subject and sentence. Then, to reduce the complexity of the prompt prediction space, we developed a novel clustering technique that automatically generates and labels clusters of words based on their shared semantic meaning. And then we color the predicted tokens from the LLMs by their cluster label in each visualization. And finally, we provide several expressive and interactive text visualizations that promote exploration and discovery of insights at multiple levels of data abstraction in a heat map, a set view, and a scatter plot. So the heat map makes it easy to accurately identify and compare individual probabilities across prompt variations, like in the columns, and the semantic clusters, which are in the rows. The grid structure will uniquely highlight words not shared between prompts with that empty space, which helps users find outliers. The set view, inspired by parallel tag clouds, facilitates in-depth comparison of word sets across multiple prompts. So the prediction likelihood is encoded to the word size, And the users can then reorder the lists by name or rank, just like in parallel tag clouds. When sorting by rank order, selecting a predicted word will highlight all occurrences across the lists and align them vertically. And the gray lines will encode the number of predictions that are higher and lower in the rank order list, which will then reveal patterns in the rank order, such as things that are predictions that are more or less likely to occur for certain sentences. And finally, the scatter plot projects predictions in a low-dimensional space and then uses a dust and magnet interaction to position the prompts as points of interest that can be dragged. And this will reveal new relationships between predictions as they shift towards more or less likely prompts to occur in. So, for example, common predictions, which are more relevant to a subset of prompts, as well as unique predictions that share a relationship, let's say between like two prompts, they tend to visually group, such as sharing the line between 2 points of interest. And so overall, collectively, our visualizations help users identify the likelihood and uniqueness of individual predictions, compare sets of predictions between prompts, and summarize patterns and relationships between predictions across all prompts. So we use Knowledge Viz to evaluate 5 BERT-based models on 3 different tasks: eliciting biomedical knowledge in fine-tuned models, producing identity stereotypes, and testing for common sense knowledge. So the heat map revealed that effects of grammar tended to change results in the biomedical evaluation. And this is really concerning to see that biases on the grammar overshadow whether the answer was actually correct from the model. So for example, SciBERT was more sensitive to subject replacements. And so it would often ignore the grammar or phrasing changes in the sentences. Now, SciBERT uses a custom vocabulary so that we suspect that this could raise issues with using out-of-domain words as those subject replacements. Whereas PubMedBERT was more sensitive to the changes in the context and the grammar of the sentences. So it could wildly swing between something being important and necessary to easy to difficult, all just based on the phrasing. And for a medical model, this is drastically decreasing confidence in the robustness. Using the set view, one of the most concerning identity stereotypes that we observed in BERT were associations with negative stereotypes and being Jewish. And another was a lack of Hispanic and Latino American representation, as common predictions for Asian, African, and European Americans that would occur were missing for this group. And so one reason could be a lack of representation in the training data for BERT. Roberta exhibited stronger biases towards groups of identities. So the scatter plot helped reveal groupings of shared predictions between the subject replacements, such as stereotypes of oppression, violence, and corruption between Islam and Hinduism, violence, brutality, cruelty, and murder between fascism, communism, and nationalism, and moderation, stability, bravery, and peace between conservatism, liberalism, and democracy. And when looking at these in particular, predictions, again, that share an edge often reveal very unique associations that are difficult to otherwise detect and discover. And finally, a recent trend in privacy and safety is looking to make LLMs smaller with the same performance. And so we compared reasoning capabilities between BERT, a big model, and DeSilbert, a little model. And so the scatter plot was useful to understand semantic groups of predictions across replacements. And in general, we actually found DeSilbert performed pretty similarly to BERT, which is good news for smaller models. And we then ran an expert evaluation with 6 academic NLP researchers and engineers. All of them had experience with training or adapting transformers for their research, and they were given an hour to explore the interface and provide feedback either on the evaluation data set or on their own examples. So participants uncovered several insights. For example, P5 found that BERT and Roberta both often ignored semantics in very obvious places. And P3 identified both grammatical issues as well as a lack of negative associations, like not, when using out-of-distribution vocabulary on PubMedBERT. And this caused them to question kind of the assumptions about how these models were trained. The visualizations were praised for their logical progression. This helped P1 kind of unpack the data in increasing amounts of detail. But P6 noted that a minimum number of prompts and predictions may be needed to increase the confidence in the patterns being observed. And P2, who was training LLMs on physics lectures and textbooks, suggested using Knowledge Viz for examples like testing for domain-specific concept learning, like can the LLM reproduce force equals mass times blank? And all participants felt that knowledge viz helped kind of open the black box of how LLMs work, especially for rapid qualitative evaluation. And so how can knowledge viz be used to close the loop of evaluation in NLP? And we saw 3 scenarios emerge. Well, the most common use case was using knowledge viz to augment training data with examples through rapid prompting and evaluation. Another emergent task was comparing models, particularly at the start of a project, where knowledge viz can make comparison of these project-specific prompts fast and insightful. And knowledge viz also encouraged deeper analysis of harder to identify biases, which are usually ignored as edge cases, such as those at the intersection of identity groups. And finally, as language and models usage shifts over time, we really want to encourage analysis to continue even after these models are deployed to continue uncovering potential harms. And finally, there's several avenues for future work. One is enabling selection and visualization of subsets of predictions to do a more fine-grained analysis and testing on effects of generation. Adding views for direct comparison of models within the interface, and also potentially leveraging generative LLMs to seed the prompting interface. So knowledge viz is live and open source at the QR code above, and I hope you all will give it a try. Thanks for listening.
All right, thanks for the talk. I see one question on Slido. It's a technical question. What factors decide the font size and ranking in the parallel text cloud?
Well, that's a good question. I have it right here. So in the set view here, the model itself returns the likelihood score for each prediction for its vocabulary, because it runs a final layer over top that will like assign a probability of predicting a certain word. So we take that probability and assign that directly to the size. The ordering is simply either by vocabulary, by alphabet, or by the rank order. So it's like if one probability is higher than the other, we just kind of sort them by either by the name of the rank order or within the groupings that we have for the clusters. So it's user set.
Okay. Now I have a question. Maybe a quick question. I'm sure you've been asked this a lot. Have you applied this to newer like GPT large language models? What have you found between all those models and different versions of those models?
Yes. So this work has been in review for a very long time. I think you saw it was like 2021 when we were testing this all out. So a lot of people have been asking, well, yeah, how does ChatGPT do? How do the generative models do? They don't exhibit as many of these biases as we used to see. So I think one of the ways I like to answer this is to say that older models like BERT are still some of the most popular models still being used for a lot of tasks. So I think that idea that we had of being able to retest models and not just kind of assume that they're outdated because they get used a lot is actually really important. So I haven't done a lot of analysis of the newer ones, but for the ones that are still being embedded in very older systems that are still being used, I think it's good to go back and look and say, did we miss anything? Especially those edge cases, which I think knowledge viz makes it really easy to find, which was like these intersectional identities and stuff, which are kind of hard to test otherwise.
Yeah, great points. Thank you. Thanks again, Adam.
Of course.
All right, Leilani, please prepare to share your screen. Our last but not least, last presentation of the session is what do we mean when we say insight? A formal synthesis of existing theory. So our presenter is Leilani. I'll let her introduce herself and her co-author. Okay, we can see your slides. I think you're on mute, Leilani. There you go.
Okay, perfect. Thank you. And you can see my slides?
Yep.
Okay, fantastic. So I'm Leilani Battle, an associate professor at the University of Washington. This research is in collaboration with Professor Alvita Otley from Washington University in St. Louis. So in this talk, I'll motivate the need to define insights. I'll summarize existing definitions from the literature. I'll show how we unify these definitions through a new formalism and toolkit, and I'll briefly touch on some usage scenarios and future research directions. So first, you might be wondering, why does it even matter what the definition we use are for insights? And my answer is we tend to design systems and studies based on what we believe insights are. For example, if insights are spontaneous ideas, then we might lean towards building tools that allow people to express themselves creatively. If insights are statistical properties, then we might focus on designing tools to mine statistics and facts from data sets. If insights are units within a knowledge base, then we might lean towards building knowledge management interfaces. And together, we see that our definition of insights plays a critical role in understanding what tools we build and why we build them. Now, how are insights actually defined in the literature? So we conducted a comprehensive literature review of papers analyzing, defining, and capturing insights, which yielded 42 papers for our analysis. And I'll share 2 key findings from this literature review that informed the design of our formalism. So we find that the literature tends to define 4 types of insights: utterances, data facts or statistical properties of a data set, hypotheses or testable questions or assertions over a data set, and knowledge links or units of information with directed or undirected edges between them. But the units and the links were inconsistently defined in the literature. So with all these different definitions, how can we specify insights in a consistent way? And another question we have is, could we unify these definitions? Are we really committing to something different when we pick one definition over another? So our answer is yes, we can unify them, and we contribute a new formalism for this purpose. Now, what does this formalism look like? So the second finding of our literature review is that different definitions actually seem to be describing parts of the same cohesive whole. So what our formalism does is map these different components that these definitions touch on into a single unified data structure. And I'll summarize that data structure here. So first, insights tend to start with the extraction of data facts from an input data set. Then these data facts are aggregated into broader generalizations about the data set, which in turn can inform potential hypotheses for further analysis. Then this analytic knowledge, or the information we extract from the data set, is linked with contextual knowledge that gives those results meaning. Now, what does this look like in practice? Let's walk through an example. Let's say we're exploring some cars data, and we're interested in identifying efficient cars. We can start with analyzing available data. So here we're visualizing horsepower versus miles per gallon to estimate a car's efficiency. So here we see a more complex relationship or a correlation between these variables. But to keep the story simple, let's say we want to test this correlation with, say, a linear regression. And this captures our current understanding of car efficiency. In parallel, we might search for domain knowledge on the topic, such as articles written by car enthusiasts or industry experts. And we can keep track of the different concepts that are focused on from these information sources, such as car manufacturing or car production. And we might even have our own experience that we can rely on with cars. I don't, but maybe other people in the audience do. For example, maybe people are familiar with car design. Say the number of cylinders in the car's engine. So together, this knowledge might lead us to a certain hypothesis, say that US cars are less efficient than Japanese cars. And this is a hypothesis we can explicitly test on the data with a model. For example, here, a decision tree. But there could also potentially be confounders, like I mentioned, the number of cylinders in the car's engine. So our formalism defines insight, the insight discovery process, as building a graph of knowledge that spans multiple information sources. And by defining insights in this way, using knowledge graphs, our formalism can draw on ideas from data mining, data management, and knowledge management. And then we also implemented this formalism as a toolkit called Pixis for specifying insights in TypeScript and JavaScript. So for sake of time, I'll just give a couple of brief examples and discuss usage scenarios for the implementation Pixis. Let's start with how we incorporate analytic knowledge into a knowledge graph using Pixis. So let's start with our linear regression example here. So what we do is we specify the kind of data relationship that we want to capture, here, linear regression. And the important part in this specification is to know what the input and output variables are to that relationship. So then we take this information and embed it within an analytic knowledge node in Pixis. So we note the data source, we reference the data relationship, and then we can add an optional note, if we like, about the purpose of the node. If we also have some pre-processing we want to do beforehand, we can include those data transformations or those data queries as well. And this is what the code looks like in Pixis. Now, what about domain knowledge? How do we incorporate that into Pixis? So here we have domain knowledge nodes and an article that we want to include. To build our nodes, we note the concepts that are associated with that article. We can give the node a name. And we also link the sources that we are relying on. And we can have more than one source linked to a node. But for simplicity, let's just focus on one. Here's what this code looks like in Pixis, where we're storing the source information using a JSON format. All right, now let's specify a full insight. So here are 3 analytic and domain knowledge nodes, which I just showed you. How do we, and then here are the contents of each node. How do we build these into an insight? So in Pixis, we have insight nodes. And then what you do is you link the knowledge sources that are relevant to that node. So you can think of insight nodes as being aggregate nodes. And then again, we can add an optional note about this node's purpose if we want. And this is what the code looks like in Pixis for specifying this insight. All right, what can we do with this formalism? I'll share a couple brief examples. We have more examples in the paper as well as in our GitHub repository. So one example of using our formalism is that we can re-implement insights from the literature using Pixis and generalize what we find into templates. So here we're replicating insights from Chris North's paper, Defining Insights, where we see different data transformations and relationships being described over housing data. And here we're seeing insights defined with increasing complexity, where complexity is being dictated by the number of data transformations or the complexity of the data relationships being expressed. And what's interesting about this is it allows us as a community to have a richer discussion about what it means for insight to become more or less complex. So another example here is we can compare insights observed across multiple studies. So here we have a study that specifies insights in a JSON format on the left, and then one of my previous studies specifying insights using natural language text descriptions on the right. So at first glance, these insights look wildly different, but as it turns out, when you implement them both in Pixis, they have the same underlying structure, which you see in the bottom row here. In particular, we're seeing basically aggregate data queries, where we're doing quantitative binning to do our aggregation on the left and nominal binning to do our aggregation on the right. So again, with the original insight formats, they look completely different, but they look strikingly similar when you integrate them into Pixis. All right, what about future research? Well, here are a few ideas. We can develop insight corpora similar to the interaction log datasets we regularly collect in our community. We could generalize these corpora into templates for generating recommendations in the future. We could develop new insight discovery tools based on the principles behind the formalism that we contribute. And also we could develop insight validators to detect logical and statistical fallacies in specified insights, similar to prior work. As an example, as it turns out, the number of cylinders in a car's engine is predictive of its origin, and a validator could catch these potential confounders. And this is just a few ideas of how you could use the formalism in the future. Yeah, and thanks so much for listening to the talk. I'm ready for questions.
Okay, thank you, Leilani. We have a few questions coming in. Let me maybe read one of them. Do you have any suggestions on how to evaluate the potential insights that could be gained from our visual representations or visualization systems?
Yeah, absolutely. So there is some work on this in the past. For example, you could look at if someone is interested in data relationships or correlations or even causality, you can use existing work to evaluate whether or not that correlation actually exists in the data. If people are making hypotheses about, A implying B, or when we see condition A, B happens, you can test those, assuming you can infer the correct model of what the user is trying to analyze. So there are some statistical assumptions that would have to be made, but that's one way that you could do that as well. Another opportunity could be to search knowledge graphs for relevant contextual information and to see if the contextual information matches what's being seen in the data or not. That could be another possible way to validate and I think would be interesting future work. The database community is interested in this kind of work, basically querying knowledge graphs and also integrating knowledge graphs with data tables and data discovery or dataset discovery as well. So yeah, I encourage folks to also consider, sorry, I'll put this here.
Okay.
I encourage folks to consider work in other communities as well.
Yeah, I see an avalanche of questions coming in. So please take them to with Discord and answer those questions. Okay, let's wrap up the session. We're at time. Thank you to all the presenters who shared their exciting work, and for those tuning in on YouTube live stream. Thank you so much for attending this session, and enjoy the rest of your conference. All right. Bye-bye.